Doping is the addition of an impurity into the lattice of a semiconductor to increase its conductivity by modifying its electrical properties. To understand doping, we must first consider the band theory of solids. We know that for a solid to conduct electricity, electrons jump from the valence band to the conduction band. They must overcome the forbidden energy gap, as electrons cannot exist in this energy band. In a semiconductor, at room temperature, the conduction band is partially filled and its conductivity is moderate. If heat is applied to a semiconductor, the electrons can gain thermal energy and jump up from the valence band to the conduction band. This is possible because semiconductors have relatively small forbidden energy gaps. When an electron in the valence band jumps up into the conduction band, it leaves behind a positively charged hole. For example, if an electron in a semiconductor gains heat energy and jumps to a higher energy level, it leaves behind a positively charged hole, which attracts other electrons and facilitates movement of charge in the semiconductor. When an electric field is applied, holes move in the same direction of the field and electrons move in the opposite direction of the field. This will produce a current in the direction of flow of positive charge. The addition of an impurity into a lattice will cause the conductivity of a conductor to decrease. This is because the number of electrons in the conduction band is already at a maximum, so an impurity will only cause collisions between the electrons. If an impurity is added to a semiconductor, its conductivity will increase due to an increase in the number of negative electrons and positive holes. An intrinsic semiconductor is a pure semiconductor, so the number of holes is exactly equal to the number of electrons. An extrinsic semiconductor has had an impurity added to it, so the number of holes is not equal to the number of electrons. The addition of about one impurity in 100,000 silicon or germanium atoms is known as doping. There are two types of doped semiconductors, N-type and P-type. We will start with P-type semiconductors. If we consider a silicon atom, we know it has 4 valence electrons, as it is a group 4 atom. When a group 3 element, such as boron, is added to a semiconductor such as silicon, because silicon can make 4 covalent bonds and boron only has 3 valence electrons, there is a positive hole. This means that there are extra holes in the valence band which can carry charge without the need for an electron to jump into the valence band. A small new energy level is created, known as an acceptor level, as there are now extra holes where electrons can fill these positions. When a voltage is applied, conduction occurs more easily as electrons can easily move to the positive holes. We will now discuss N-type semiconductors. N-type semiconductors are formed when a group 5 atom such as phosphorus is added to silicon. Again, considering that silicon can make 4 covalent bonds, as phosphorus has 5 valence electrons, when the covalent bonds are formed there will be 1 extra electron. There are now extra electrons in the conduction band without the need for them to jump up from the valence band. A small new energy level is created, known as a donor level, as there are now extra electrons which can easily move into a hole. When a voltage is applied, conduction occurs more easily as there are more electrons able to conduct electricity. It is important to understand that doped semiconductors have an overall neutral charge, as the number of overall protons and electrons remains equal. For example, the addition of boron does not make a semiconductor positively charged, as there are still the same number of protons and electrons. There are many applications of doped semiconductors. Considering that P-type semiconductors lack electrons and N-type semiconductors have excess electrons, if a P-type and N-type semiconductor are joined, a p-n junction is formed. In a p-n junction, the extra electrons in the N-type semiconductor migrate to the extra positively charged holes in the P-type semiconductor. The N-type semiconductor becomes positively charged due to its loss of electrons, and the P-type semiconductor becomes negatively charged due to its gain of electrons. This positive and negative charge at the p-n junction is known as the depletion zone, and this creates a potential difference. In summary, doping is the addition of an impurity into the lattice of a semiconductor with the aim of making it more conductive. Thank you for watching.